So I want to talk about higher order measures. By definition, measure is something which is contained in the signal. And the idea is that perhaps you will measure some of those measures. And since those are higher order measures, even though they are present in the signal, hopefully, no matter what's the engine, but as we move to these higher order measures, higher order just in the sense of Taylor expansion, if we can measure those, we are moving closer to the engine, and perhaps we will learn something about it. But probably I don't have to tell this to this audience if one can invent or present whatever a new measure, and if this measure can indeed be observed, this is a big step forward, no matter what this measure means. So this is mostly for me, not for you, because I'm not working in this field. So there is this FRB engine, which perhaps is a trefoil. And when it reconnects, it produces a 1 millisecond 100% linear signal, 100% linear polarized signal. But an ideal telescope at Earth, ideal telescope means 100-second observation, 10 gigahertz frequency, all the way from 0 to 10 gigahertz, and each reading occurs, let's say, 100 times per 0.1 nanosecond. So like real lifetime electric field, two-dimensional electric field vector as a function of time with very, very high resolution. What?
Easy.
Yeah, I don't know. I don't care. So an ideal radio telescope will not observe what central engine has produced. It will see something lasting for many seconds, almost unpolarized. And to get something, we need to really analyze this very high resolution signal. That is to say, we need to get rid of all this dirt, dispersion measure, rotation measure, to see to the center of the machine, and thereby understand. I cannot even spell it. So with this philosophy, what I am going to discuss is just some more sources of dirt. Second, dispersion measure, conversion measure, and nonlinear measure. But what's dirt and what's the goal is not quite clear. I think the following anecdote here is appropriate. The biologist Timofeev Rysovsky, when asked what does he think about the origin of life, like the origin of FRBs, answered allegedly, I do not know, I was not there at the time, ask Aparin. Aparin is a much older famous guy who offered his version of the origin. So I very much agree with the philosophy of Sterl Feeney, Ellie Waxman, and all other cynics who say that we were not there. It's very hard for us to guess correctly the true central engine of this machine. But part of the answer of this biologist, Timofeev Rysovsky, had this positive program in it. Basically, he was saying, we should not think about the origin of life. We should rather subject fruit flies to various levels of radiation and see how they respond. Likewise, here, I think observers should look for new measures just blindly in their signals, just to see identify some new patterns. Of course, I'm not telling you what to do. This would be ridiculous. But if I could, I would say, look for new patterns other than standard rotation measure, dispersion measure, and stuff like that. And theorists should forget about distinguishing trefoil knot from Hopf-Flink, but rather see what kind of signals can be ascertained no matter what the engine is. And if those signals are found, so much the better. So what are all these measures? They are really Taylor expansion with respect to inverse frequency of the wave. Dispersion measure is the leading order term. Rotation measure comes later. Those are characteristic plasma frequencies. Conversion measure, naive, comes later. Second dispersion measure, I don't know what's the right terminology here. Do you call this second dispersion measure? Second term, whatever. So second dispersion measure is okay, right? Formally, yes, but what I'm interested in is the fact that lower frequencies are not as much delayed as predicted by the first dispersion measure, okay? So I would, and then naive, I will explain later why I call this thing naive. And then, of course, there is some kind of a nonlinear measure which accounts for the fact all these were for linear waves, and that's why we have, I would say, perfect understanding of those. This is a to be introduced nonlinear measure, which should be there simply because closer to the source for things as bright as FRBs, this becomes large, this expansion parameter, and of course everything should be integrated along the line of sight. So I would assume that the second dispersion measure is routinely measured by you, but I have never seen it reported before. Maybe we can discuss it during the discussions. I'm especially, Sterlfini yesterday said, if I can repeat him correctly, that today we can measure this dispersion measure with the accuracy as small as as good as 0.001 parsec times centimeter minus 3. Am I quoting you correctly, Sterl?
For the right sufficiently.
For the right sufficient. So I would find it strange that at the accuracy of 0.001 you would not be able to detect the second dispersion measure. But like I said, just I want to make sure that each time you are dealing with the data, you are trying to measure it, because it is absolutely there theoretically. So the attempts, I think, should be made. I will talk about conversion measure and nonlinear measure. So for me, the conversion measure story started during a wonderful FRB Weizmann workshop 1 year ago. And there, my hero, Harish Vedantam, gave a talk about conversion. This was the first time I heard about Faraday conversion. And I thought it was very interesting because it was like, nobody was talking about it, but he did some estimates, and apparently it was it was doable for FRB 121102 because of the very large rotation measure and some estimates, and also from papers by I think what's your name? Ben. Papers by Ben and Ellie. We had some sense of what are the characteristic fields and densities over there, so we were able to predict how much conversion should occur. And there is, however, some subtlety in this conversion measure. Probably most of you know about this subtlety, at least by now. The subtlety being, if you have a high rotation measure, it means that your electric field is rotating like crazy. If it keeps, as the wave propagates. So if this thing is rotating...
Folks online, if can you make sure to
mute? If this thing is rotating like crazy, it will have hard time Faraday converting.
If you're on Zoom, please mute.
Thank you, sir. So if it is rotating like crazy, oh, it's me. Really? Oh, no? Yeah, that's the problem with the engines of GRBs. Any plasma being turbulent will automatically produce radio waves, like, so, for example, thunderstorm, okay, or all these solar radio bursts and so. So anyway, so it is rotating like crazy because of high rotation measure, but then if linear polarization is pointing different directions all the time, it would have had time converting into circular polarization, because it will be producing circular polarization of one sign this time, this time, this time. So you need to kill adiabatic. You have to become non-adiabatic. That is to say, you have to go to the place where your normal Faraday rotation is really slow, and at those places where you kill Faraday rotation, you will be able to do Faraday conversion. And so once we realized this thing with Yuri Levin, I think we wrote a correct paper. And since it is correct, I don't need to discuss it too much. I will discuss a wrong paper I wrote later. So, but the point is, if this is magnetic field as a function of the line of sight, and suppose your plasma density is only here, then only near the points where the parallel magnetic field vanishes, you are able to do conversion from linear to circular polarization. As a result, if you illuminate this magneto-ionic environment, as you call it, with linear polarized waves, the resulting, so here it's shown for FR, this is fiducial, I mean, I'm not sure it's 1 gigahertz, it can be 500 megahertz or something like that, but these numbers are semi-realistic. So this is a prediction for FRB 121102. If you can measure it very well at gigahertz frequencies, the resulting Stokes V parameter, the circular polarization, will vary quasi-periodically as a function of frequency. There will be two, if you do now Fourier transform frequency with respect to the frequency, you will have two peaks. Each peak for each magnetic field 0. So there are as many conversion measures associated to FRB, as many zeros along the line of sight the magnetic field had. So you have just a single rotation measure, but you have 2 or 3 perhaps, or 0, if magnetic field is nowhere 0, 2, 1, 0, 1, 2, 3, 4 different convergence measures, each characterizing the 0 in the parallel magnetic field. So, like I said, the paper is there. Since it was written together with Yuri Levin, it is very clear. You can just read it and hopefully use it. Or whatever, probably you should not read it. When you will detect this, then you should read it, and then the paper can be used to write. Why waste your time? You just measure this first. So, like I said, since it's right, I will not talk about it. I will talk about what's wrong. This nonlinear scattering of fast radio bursts. This is a paper containing glaring error, which I recently published. I will replace it soon. Again, my hero Harish yesterday explained to me my glaring error, but that's okay. So here is the idea. Amplitude, wavelength, vector potential properly normalized. We will call the wave nonlinear when this vector potential becomes order unity. For FRBs, it happens at about, let's say, 10 to 13, 10 to 14 centimeters away, 10 to 15 perhaps centimeters away from the magnetar. So when this becomes over the unity, should I stop?
Well, we're getting into question time now.
Okay, let's stop right now.
Okay.
Huh?
Yeah.
What?
What's the punchline?
Yeah.
Oh, okay. Right, if I may.
Sure.
There are.
What's the rest of your talk?
Right. So there are two punchlines here. The punchline, both perhaps mostly addressed to theorists. So the first punchline is that nonlinear electromagnetic wave is not as scary as it sounds. If you choose your geometry properly, namely planar linearly polarized wave in an electron-positron plasma, which was initially zero temperature and then magnetized, the resulting equations for nonlinear waves become very, very simple. This is just Klein-Gordon with varying mass, which is the mass, of course, being the density. The density is because electrons and positrons are pushed by the electromagnetic wave. This is as simple as it gets. Since this is so simple, this can be studied theoretically and later on numerically. The result is that this nonlinear wave is unstable all by itself. It's nonlinearly unstable. These particles, when they move with respect to each other with high amplitude, spontaneously bunch. Just a linear wave, nothing. In this electron-positron plasma, it will spontaneously form bunches of particles, and as a result, a wave which was initially monochromatic will develop this highly intermittent spectrum. The glaring error I referred to was my interpreting this. So this was my proposal for the nonlinear measure, the intermittency of the spectrum. And I, in that paper, claim that 50 kilohertz coherence length seen in FRB 121102 can be interpreted as the nonlinear measure, as the result of nonlinearly modulating plasma and thereby producing the this very small scale time structures with 50 kilohertz coherence length. Any educated radio astronomer knows that this is in fact not the nonlinear measure, but rather the scattering measure. Okay, especially as Harish explained to me, for this particular line of sight, they know that this is exactly what's expected. Now, you can ask, if this is so wrong, why are you telling us about it? Because who cares, this particular experiment? The wave is still unstable. It will produce intrinsically intermittent spectrum. So the real punchline, and this will be my last thing. So the real punchline, so I have calculated the growth rate. As you see, I indeed got, this could be gigahertz from my theory. I just didn't know that there is a scattering measure. And clearly when you see this, and then you see your pictures, you say, okay, I've invented nonlinear measure. But the real punchline is here. Blah, blah, blah. We need to better understand nonlinear radio waves as regards their observational properties, signatures. One needs to invent nonlinearity or nonlinear measure, which is guaranteed to be there. The equations are simple. It's just, maybe I'm just not smart enough to identify a good nonlinear signature. But equations are simple. It's hard to believe that it is not there. And so to summarize, I hope, at least for me, because I personally don't care much, is it accretion-induced collapse of white dwarfs or magnetars? But if we can invent a new measure which will be routinely used in radio astronomy, and it does not seem like it is too high a call, if that can come out of these FRBs, I think it would be a real achievement. That's the punchline.
Great. Let's thank Andrei.